WebAssign Week 9, Problem 7. Last problem of the bunch, but it's kind of a doozy. Let's start by drawing a good picture. So we've got this loop, rectangular loop next to a long straight wire with current flowing in it. The current in that long wire is changing with time. So there's some kind of formula that would describe that. All we're told, though, is that the rate of change, that let's write it in calculus terms, di dt is, in my case, 15 amps per second. So it's changing at some steady rate. The current is ramping up, increasing slowly. That current will cause a magnetic field, and some of that magnetic field goes through this loop here. If you think about which way that's going, you're going to have dots on this side and more dots closer to the wire, and on this side you're going to have X's because the magnetic field is going into the page. And let's draw just a whole bunch more of these things to indicate this magnetic field that is getting progressively weaker as we get further away. And that makes it a little bit hard for us to calculate the flux. You'd like to say that we're trying to figure out what current flows in this loop. That current is caused by an EMF driving the current around the loop. To figure out that EMF, we would like at some point to just say the EMF is the rate of change of flux. But how do we get the flux? The flux, normally, we would say something like B times A, but that's only where B is uniform. Here, B is varying. And so we have to say that the flux is this integral of B dA. We don't have to worry about the direction. You don't have to say B perpendicular because this loop is parallel with the wire, and the B field is going to be exactly perpendicular to that everywhere. So B perpendicular is the same as B everywhere. That makes that part at least easy. But trying to get the total flux here is hard because the B field is strong close to the wire and weaker further away. We know how that behaves. We've done that last week already. The B field in general in something like this looks like mu0 I over 2 pi r. That's how the B field varies near a long straight wire. So we know exactly how it behaves, but how do we carry out this integral down here? Well, as I said in the problem, they've sort of set up some of it for you. You might back up and just say, oh well, we can't just take B times A because we don't know what B to put in there. I guess you could smell the aroma of an integral coming at that point, because the B field is varying all over there. So we're going to have to somehow divide the problem up into pieces. And you might think of doing slices of some sort. Of course, horizontal slices wouldn't make any sense because you'd still have the variation within each slice. But if we make a slice that goes vertically, slice up this into pieces, then within one of those slices that has a small amount of area dA, then we wouldn't have any variation. The B field we would know because we'd know what R to put in. It would just be that distance right there. And in fact, they have already named an integration variable R for you in this problem. It's a little dangerous because you've got R already sneaking into the problem, but they've done it right, so it works out. And then the thickness of the slice is dr. If you want to connect this to the way we usually do things, I would be saying, well, that total flux is equal to an integral of little pieces of d flux. And d flux, where my usual formula is b times a for flux, a little infinitesimal bit of flux is a b times dA. The B field is still substantial here. That hasn't changed. It's just become more clear. But the area of that slice is, in fact, infinitesimal, hence the dA that exists right there. So now to carry on with the integral, we should express everything in terms of the chosen integration variable r. They already chose that for us. See if we can get this flux. So if that's our integration variable, we've got to express b in terms of it. That's done here. And then we've got to express dA in terms of either that variable or its infinitesimal. So b is already expressed in terms of r. That's fine. But how about dA? dA is the little bit of area of this slice right here. Think about that. In the problem, there's more labeled here than I have shown. This distance is A, and I think the bottom of the loop is a width W, and the other dimension of the loop is a length L. So now you have to figure out, well, what's the size of this little rectangle right here? We're dividing this all up into tiny little rectangular slices, and they would be L in height, I guess you could say, or length, and their width is just dr. So this would be L times dr. So putting all of that in, substituting in both, we would have the integral then of mu 0 I over 2 pi r, and then L dr. That would be our new flux. This is getting ready to integrate. We could do a few more things to it. We could simplify it and say, can we take some constants out of here? Notice that I is actually changing with time, but that doesn't matter. The integral is over r, not t. So the fact that that varies with time doesn't really matter. For the purposes of the integral, it's a constant. So let's simplify this as much as we can. We can take mu 0. I is a function of time. It's a constant for the purposes of the integral, divided by 2 pi. L will also come out of here. And then we'll be left with the integral of dr over r. Let's see if I've got all the right pieces there. I think I do. We should probably put limits on the integral. Think about r. R is the distance from this long wire to the particular slice. We're going to imagine slicing this up into different slices. Some would be enclosed, some would be far away. What would be the value of r? And it's the smallest it can be. Well, it would just be this distance a down here. And then it would get up to the other edge. It would have the value of a plus w. So r goes from a to a plus w. Then, well, I guess now it's time to integrate. So mu 0 I of t L over 2 pi. What's the integral of dr over r? Maybe you remember that. You should. You learned it sometime when you took calculus. Integral of dr over r is ln. It's the natural logarithm of r. And then we evaluate that from a to a plus w. So we're going to have mu I of t L over 2 pi, and this would be ln of a plus w minus ln of a. Okay, and we could simplify this just a little bit. I'm not sure if I want to bother or not. I guess I will. Mu 0 I of t L over 2 pi. Do you remember that when you subtract logarithms, that's the same thing as taking the logarithm of the ratio, a plus w over a. It just looks a little simpler to write it that way. And that's our flux. Now we can get the EMF. The EMF is the derivative of that flux. Now we're taking a derivative with respect to time. So now when you look at this whole expression and ask what's varying with time, it's only this I right here. Everything else in this is a constant with respect to time. So I'm going to sort of move everything out in front. There is a minus sign here, by the way. And keep mu 0 L over 2 pi ln a plus w over a. And this I of t I'm going to put clear down here. This now is the derivative of I with respect to t, which we're told at the very beginning of the problem. It is ramping up. The current is changing at a steady rate, and that's what that di by dt is. Now, we were trying to get the flux, then we differentiated to get the induced EMF. Now we want to get current. That's the thing we're finally asked for, is what current is flowing around in the loop. And current around a loop like this is just the EMF that is applied to the loop divided by the resistance of the loop. The EMF induced. And so this will just be the same expression with an R in the denominator. So mu 0 L over 2 pi 1 over R ln of a plus w over a times di by dt. That should get you the answer. I haven't put the numbers in, but I'll leave that to you.